At 09:15 hours on November 24th, Major Robert Morgan leveled his Boeing B-29 Superfortress at 32,000 feet over Tokyo, Japan. The aircraft, named Dauntless Dottie, was leading 111 bombers in the first raid on Tokyo since the Doolittle raid in April 1942. Morgan could see the city clearly through the bombardier's window 13 miles below, laid out like a map under clear skies. Inside the cockpit, the temperature was 72 degrees Fahrenheit. Morgan and his co-pilot wore standard flight suits, no heavy winter gear, no oxygen masks. Outside, the temperature was minus 55 degrees Fahrenheit. At this altitude, without pressurization, the crew would have been dead in minutes from hypoxia and cold. But the B-29's cabin was pressurized to the equivalent of 8,000 feet altitude, comfortable enough that men could work normally for 8 or 10 hours. This was revolutionary. No other bomber in the world could operate at this altitude with the crew in shirt sleeves. Behind Morgan in the forward cabin, the navigator plotted course corrections, the flight engineer monitored engine instruments, and the bombardier prepared for the bomb run. In the aft cabin, accessible through a pressurized tunnel over the bomb bays, the radar operator tracked ground features on his scope, while 4 gunners monitored remote-controlled turrets. This crew integration was possible only because of pressurization. Earlier bombers flying at high altitude required crew members to wear oxygen masks, continuously making communication difficult and causing fatigue after 2 or 3 hours. The B-29 crew could talk normally, drink coffee, eat sandwiches, work efficiently for the entire mission. Japanese fighters appeared at 09:27 hours, climbing desperately toward the bomber formation. The interceptors were Nakajima Kai-44 Tojos and Kawasaki Kai-61 Tony, both theoretically capable of reaching 32,000 feet. But at that altitude, their engines struggled for power in the thin air. Their rate of climb had fallen to less than 500 feet per minute by the time they reached 30,000 feet. The B-29s were already passing overhead at 32,000 feet, cruising at 220 miles per hour, well above the Japanese fighters' operational ceiling. A few fighters managed to climb high enough to make firing passes, but their performance was degraded so severely that accurate shooting was impossible. Controls were mushy engines, overheated guns froze. One Kai-44 attempted to attack Dauntless Dottie from the front. The B-29's central fire control system detected the approach at 2,000 yards. The upper forward turret, controlled by the gunner sitting in the aft cabin, tracked the fighter automatically through the General Electric analog computer. When the fighter closed to 1,000 yards, the gunner fired. 4 50-caliber machine guns sent a stream of tracers toward the Kai-44. The fighter broke off, diving away trailing smoke. Whether it was hit or the pilot simply recognized he could not press an attack at this altitude was unclear. Either way, the result was the same. The B-29s continued unmolested to their target. At 09:32 hours, Dauntless Dottie's bombardier released 10,000 pounds of incendiary bombs over the Musashino aircraft engine factory. The bombs fell for 42 seconds before impacting the target area. Morgan banked left, joining the formation, turning southwest toward the coast. The mission continued for another 6 hours. The B-29s flew 1,500 miles back to their bases in the Mariana Islands, cruising at 28,000 feet above weather, above fighters, above anti-aircraft fire effective range. They landed at Saipan after 13 hours airborne. Most crews reported they were tired, but not exhausted, ready to fly again the following day, if required. This was what the B-29 had been designed to do: fly higher, farther, and faster than any bomber before it, operate where enemy fighters could not effectively intercept, deliver bombs with precision from altitudes that made anti-aircraft fire largely ineffective, and do it all with a crew that could function normally throughout the mission. The B-29 Superfortress was the most expensive weapons program of World War II, exceeding even the Manhattan Project that developed the atomic bomb. The program cost $3 billion between 1940 and 1945, equivalent to approximately $50 billion in 2024 dollars. Boeing built 3,970 B-29s at 3 production facilities. The aircraft introduced technologies that would define aviation for the next 3 decades. The requirements that led to the B-29 emerged in 1938. The Army Air Corps recognized that war in Europe was inevitable and that American bombers might need to strike targets in Europe from bases in the Americas or Africa. Existing bombers lacked the range and altitude performance for such missions. The B-17 Flying Fortress, entering service in 1938, had a combat radius of 800 miles. Reaching Berlin from England required 1,200 miles. In January 1940, the Army Air Corps issued Specification R-40B calling for a hemisphere defense weapon capable of 400-mile-per-hour speed, 35,000-foot altitude, 5,000-mile range, and 2,000-pound bomb load. These requirements were beyond anything attempted in bomber design. 4 manufacturers submitted proposals. Boeing's design, designated Model 345, was selected in September 1940. Boeing's proposal centered on 2 revolutionary technologies, a pressurized cabin and an exceptionally powerful engine. Both were unproven. No production aircraft had ever used cabin pressurization. The required engines, Wright R3350 duplex Cyclones, producing 2,200 horsepower each, were still in development and suffering serious reliability problems. But Boeing's engineers, led by Edward Curtis Wells, believed both technologies were essential. Without pressurization, crews could not function effectively at 35,000 feet for the 8 to 12 hours required for long-range missions. Without powerful engines, the aircraft could not carry sufficient fuel and bombs to that altitude. The pressurization system was the most challenging aspect. Maintaining pressure differential between inside and outside required a sealed cabin structure capable of withstanding stress far beyond normal aircraft loads. Every opening, doors, windows, hatches required pressure seals. Control cables, electrical wires, and hydraulic lines passing through pressure boundaries required sealed fittings. Wells' team designed 3 separate pressurized compartments. The forward cabin housed the pilot, co-pilot, flight engineer, navigator, bombardier, and radio operator. This compartment was 16 feet long and 7.5 feet in diameter, larger than the entire fuselage of many contemporary fighters. The aft cabin, located behind the bomb bays, housed the radar operator and 4 gunners. This compartment was 8 feet long and 7 feet in diameter. It was connected to the forward cabin by a pressurized tunnel, 34 feet long, running over the 2 bomb bays. The tail gunner position was a separate pressurized compartment isolated from the rest of the aircraft. The gunner entered through a hatch in the aft cabin, crawled through a non-pressurized tunnel for 9 feet, then entered his own tiny pressurized capsule containing just enough room for 1 man and his gun controls. Each pressurized compartment had a pressure regulator maintaining cabin altitude at 8,000 feet when the aircraft flew at 30,000 feet actual altitude. This represented a pressure differential of 6.55 pounds per square inch, moderate by modern standards, but unprecedented in 1942. The system used engine-driven compressors to pump air into the cabins. Air entered through intakes on the engine, nacelles was compressed, cooled by heat exchangers, filtered and ducted to the cabins. Outflow valves maintained pressure by controlling how much air escaped. The entire system had to function reliably for 10 to 15 hours, while the aircraft maneuvered, climbed, descended, and experienced temperature variations from 100 degrees on the ground to minus 60 degrees at altitude. Testing the pressurization system consumed thousands of engineering hours. Boeing built a full-scale pressure test chamber at its Seattle plant, installed a complete cabin section inside, and subjected it to repeated pressure cycles. Engineers discovered leaks at every possible location: window seals, door seals, rivet lines, electrical penetrations. Each leak required redesign and retest. The Bombardier's position presented unique challenges. The Bombardier needed an optically perfect window for the Norden bomb sight, but flat glass under pressure would flex, distorting the optical path. Boeing developed a compound curved plexiglass nose section with constant thickness that maintained optical quality under pressure. The nose cone became one of the B-29's most recognizable features. The second revolutionary technology was the remote-controlled defensive armament. Previous bombers used manned gun turrets. Gunners sat in the turrets exposed to cold and wind, manually aiming and firing their weapons. This was acceptable at 15,000 feet, where temperatures were merely cold. At 30,000 feet, with temperatures of minus 60 degrees, it would be lethal. Boeing partnered with General Electric to develop a completely new defensive system. The guns were mounted in turrets, but the turrets were controlled remotely by gunners sitting inside the pressurized cabin. Gunners aimed through computing gun sights that automatically corrected for range, target speed, and ballistics. The system included 5 gun turrets, 1 upper forward turret with 2 .50 caliber machine guns, 1 upper aft turret with 2 .50 caliber machine guns, 2 lower turrets each with 2 .50 caliber machine guns, and 1 tail turret with 2 .50 caliber machine guns and 1 20mm cannon. Total defensive armament, 10 .50 caliber machine guns and 1 20mm cannon. Each gunner controlled multiple turrets through a central fire control computer. The central fire control CFC gunner, located in the upper aft position, could take control of all turrets except the tail position. If a turret lost its primary gunner, another gunner could take control. This redundancy meant that disabling one gunner did not disable the turrets he controlled. The computing gun sight was an analog mechanical computer that solved the ballistics problem continuously. The gunner tracked the target through an optical sight. The computer measured target angular velocity, calculated range using a stadiometric rangefinder, computed the ballistic trajectory of 50 caliber bullets at the current altitude and airspeed, and directed the turrets to the correct lead angle. The entire process was automatic. The gunner simply kept the target centered in his sight. The computer and turret drive motors did everything else. When the guns were aligned correctly, an indicator light illuminated and the gunner pressed the firing trigger. The system was so advanced that it remained classified until 1944. When B-29s began operating over Japan, Japanese intelligence officers were mystified by the defensive fire patterns. Turrets were firing at attacking fighters before the fighters came into view of the turret's position. Japanese analysts initially theorized that the B-29 gunners must have exceptionally good eyesight, or that the aircraft carried additional observers whose sole job was spotting fighters. The actual explanation: remote-controlled turrets directed by computing gun sights located elsewhere in the aircraft, was beyond Japanese technological capability to duplicate. Japanese attempts to develop similar systems failed due to lack of sufficiently precise motors, bearings, and computing mechanisms. The engines that powered the B-29 were Wright R-33-523 duplex cyclone radials. Each engine displaced 347 cubic inches, the largest production aircraft engine in the world in 1944. The engine used 18 cylinders arranged in 2 rows of 9, all driving a single crankshaft. With turbochargers, the engine produced 200 horsepower at takeoff and maintained power to 30,000 feet altitude. The R-3350 was also the most temperamental engine in American service. It suffered chronic overheating problems, frequent cylinder failures, and a tendency to catch fire. The engine was rushed into production before development was complete, and early models were dangerous. The overheating stemmed from the engine's compact design. 18 cylinders packed into a 55-inch diameter created insufficient cooling airflow to the rear cylinders. The rear cylinders would overheat, exhaust valves would fail, and metal fragments would tear through the cylinder walls. If oil sprayed onto hot cylinder heads, it would ignite, and the entire engine would be engulfed in flames. Between February 1943 and May 1944, the B-29 program lost 47 aircraft to R-3350 engine fires, killing 312 crew members. Most crashes occurred during takeoff when the engines were producing maximum power and the aircraft was too low and slow to allow the crew to bail out. The problem became critical in June 1944 when B-29s began deploying to forward bases in India and China for operations against Japan. Engine failures increased dramatically in the heat and humidity of South Asia. Aircraft were aborting missions due to engine problems at rates exceeding 30%. Some missions had more aircraft turn back with engine failures than reached the target. Wright Aeronautical Corporation worked desperately to fix the R-3350. Engineers developed improved cooling baffles that directed more airflow to the rear cylinders. They redesigned exhaust valves using better materials. They modified fuel injection to prevent mixture imbalances. They added additional temperature sensors so flight engineers could detect overheating before catastrophic failure occurred. By August 1944, the modifications had reduced engine failure rates significantly. But the R-3350 never became truly reliable. Throughout the war, B-29 crews treated their engines with a combination of respect and suspicion, monitoring temperatures, obsessively reducing power at every opportunity, and preparing for engine failure as a routine possibility rather than an emergency. The B-29's physical dimensions reflected its capabilities. Wingspan was 141 feet, nearly the length of a football field. Length was 99 feet. Height was 27 feet. Empty weight was 74,500 pounds. Loaded weight, typically 120,000 pound maximum overload. Weight, 140,000 pounds. At maximum weight, each square foot of wing area supported 71 pounds, the highest wing loading of any World War II bomber. High wing loading made the B-29 fast. Cruising speed at 25,000 feet was 230 miles per hour, faster than most contemporary fighters could cruise at that altitude. Maximum speed was 358 miles per hour at 25,000 feet. Stall speed was 105 miles per hour, uncomfortably high, requiring long runways and careful speed control during landing. The bomb load was 20,000 pounds, carried in 2 bomb bays. Standard mission load was 10,000 to 12,000 pounds of bombs, plus 6,300 gallons of fuel. Combat radius with this load was 1,600 miles, allowing strikes deep into Japan from bases in the Marianas. With reduced bomb load and maximum fuel, ferry range exceeded 5,000 miles. The first B-29 flew on September 21, 1942 from Boeing Field in Seattle. Test pilot Eddie Allen reported excellent handling characteristics and performance that met or exceeded specifications. But during the second test flight, Allen reported severe engine overheating. He was turning back to Boeing Field when the overheated engine caught fire. The fire spread into the wing structure. The wing failed. The B-29 crashed into a meatpacking plant in Seattle, killing Allen and his crew of 10 plus 20 people on the ground. The accident nearly killed the program. The Army Air Forces temporarily suspended all B-29 test flights pending investigation. Boeing engineers determined that the fire was caused by the same rear cylinder overheating problem that would plague the R-3350 throughout its service life. Despite the setback, the program continued. The Army Air Forces needed the B-29's capabilities desperately. By mid-1943, it was clear that Germany would be defeated and the focus would shift to Japan. Bombing Japan from bases in China or the Marianas required a bomber with the B-29's range and altitude performance. No alternative existed. Production began before testing was complete, a highly unusual procedure justified by wartime urgency. Boeing operated production lines at Renton, Washington and Wichita, Kansas. Bell Aircraft built B-29s at Marietta, Georgia. Martin operated a line at Omaha, Nebraska. By mid-1944, all 4 factories were producing B-29s at a combined rate of 100 aircraft per month. The first combat mission was flown on June 5, 1944, when 98 B-29s based in India attacked railway facilities in Bangkok, Thailand. The mission was partially successful. 77 aircraft reached the target and dropped bombs. 14 aborted due to engine failures. 7 made emergency landings at forward fields. None were lost to enemy action. The mission demonstrated the B-29's capabilities and its problems. The aircraft could reach targets far beyond the range of any other bomber. It could operate at altitudes where fighter interception was difficult. But engine reliability was marginal, and the logistical complexity of supporting B-29 operations from remote bases was enormous. Operations from India and China proved unsustainable. Every gallon of fuel, every bomb, every spare part had to be flown into China from India over the Himalayas, the Humpua, one of the most dangerous air routes in the world. For every gallon of fuel burned over Japan, 7 gallons were consumed flying supplies into China. The effort was not cost-effective. The solution was to base B-29s in the Mariana Islands, captured in June-August 1944. The islands of Saipan, Tinian, and Guam were 500 miles from Tokyo within B-29 range. They could be supplied by sea, eliminating the logistical nightmare of trans-Himalayan flights. The islands were secure with no threat of Japanese ground attack. Construction of bomber bases in the Marianas began immediately after the islands were secured. CBs built 6 airfields each with an 8,500-foot runway, capable of handling B-29 operations. Each airfield could accommodate 180 B-29s. Fuel storage, ammunition bunkers, maintenance hangars, and crew quarters were built to support sustained operations. The first B-29s arrived at Saipan in October 1944. By November 11, B-29s were operational. These were the aircraft that attacked Tokyo on November 24, 1944, the mission described at the beginning of this narrative. That first Tokyo mission revealed a critical problem. Although the B-29s could fly at 32,000 feet, bombing accuracy from that altitude was poor. Winds aloft over Japan frequently exceeded 150 miles per hour, far stronger than bombardiers had encountered over Europe. The jet stream, not yet well understood, made precision bombing nearly impossible. Of the 11 B-29s that bombed the Musashino aircraft plant on November 24, fewer than 50 bombs hit within 1,000 feet of the aim point. Most bombs fell miles away, scattered by the wind. Photo reconnaissance showed minimal damage to the target. The mission was tactically a failure despite the successful demonstration of the B-29's operational capability. General Curtis LeMay, who took command of 60th Homryu Bomber Command in January 1945, made a controversial decision that would change B-29 operations fundamentally. He ordered B-29s to stop bombing from high altitude. Instead, they would attack at night from low altitude, 5,000 to 8,000 feet, carrying incendiary bombs instead of high explosives. This decision negated the B-29's primary advantages. Low-altitude operations exposed the bombers to anti-aircraft fire. Night operations made the pressurized cabins and centralized fire control less important, since fighter interception at night was minimal. The B-29 was being used in a role it was not designed for. But LeMay's assessment was correct. High-altitude precision bombing was not working against Japan. The jet stream made accuracy impossible. Japanese industry was dispersed in small factories throughout cities, not concentrated in large plants like German industry. Destroying Japanese industrial capacity required destroying the cities themselves. The first low-altitude incendiary raid occurred on the night of March 9 to 10, 1945. A force of 334 B-29s attacked Tokyo from altitudes between 5,000 and 7,000 feet, dropping 1,665 tons of incendiary bombs on the most densely populated district of the city. The attack created a firestorm that killed approximately 100,000 people and destroyed 16 square miles of urban area. The effectiveness of low-altitude incendiary attacks vindicated LeMay's decision. Over the next 5 months, B-29s burned 67 Japanese cities, destroying 178 square miles of urban area and killing over 300,000 civilians. Japanese industrial production collapsed. By July 1945, Japan's economy was approaching complete paralysis. But the low-altitude campaign came at a cost. Anti-aircraft fire damaged hundreds of B-29s. Japanese fighters, which had been largely ineffective against B-29s at 30,000 feet, achieved better results against bombers at 7,000 feet. Between March and August 1945, Bomber Command lost 136 B-29s to all causes over Japan, the highest loss rate of the B-29 campaign. The loss rate was still sustainable, approximately 1.5% per mission, far lower than the 5 to 10% losses that B-17s suffered over Germany. But it demonstrated that the B-29's invulnerability depended on altitude. At 30,000 feet, Japanese defenses were largely ineffective. At 7,000 feet, the B-29 was vulnerable like any other bomber. The B-29's most famous missions were the atomic bomb attacks on Hiroshima and Nagasaki. These missions were flown at high altitude, demonstrating that the aircraft could still operate in its designed role when required. On August 6, 1945, a B-29 named Enola Gay, piloted by Colonel Paul Tibbets, dropped an atomic bomb on Hiroshima from 31,000 feet. The mission proceeded exactly as designed. The B-29 flew at high altitude where Japanese fighters could not effectively intercept. The pressurized cabin allowed the crew to function normally throughout the 11-hour mission. The bomb was released with precision from altitude too high for accurate anti-aircraft fire. 3 days later, a B-29 named Bockscar, piloted by Major Charles Sweeney, dropped an atomic bomb on Nagasaki from 28,900 feet. Again, the mission demonstrated the B-29's capabilities in its designed role. These missions ended the war. Japan surrendered on August 15, 1945. The B-29 had fulfilled its strategic purpose not primarily through high-altitude precision bombing as originally envisioned, but through a combination of high-altitude operations when possible and low-altitude incendiary attacks when necessary. After the war, the B-29 remained in service with the newly independent United States Air Force. B-29s served as the primary American strategic bomber until replaced by the B-47 Stratojet in the early 1950s. During the Korean War, B-29s conducted conventional bombing missions against North Korean and Chinese forces, though with less success than in World War II due to improved enemy fighters and anti-aircraft defenses. The last operational B-29 mission was flown in 1960, 15 years after the end of World War II. Some B-29s were converted to other roles, KB-29 tankers, for aerial refueling, WB-29 weather reconnaissance aircraft, and various test platforms. The final B-29 was retired from military service in 1960. Today, approximately 20 B-29s survive in museums. Only 2 are airworthy. Fifi Sinunhuam, owned by the Commemorative Air Force, is based in Texas and flies regularly at air shows. Daki Kurut, restored by a volunteer organization in Wichita, Kansas, returned to flight in 2016 and also performs at air shows. The most famous B-29, Enola Gay, is displayed at the Smithsonian National Air and Space Museum's Stephen F. Udvar Hazy Center in Virginia. The aircraft was restored to its August 6, 1945 configuration and is displayed without markings or interpretation beyond basic technical information, reflecting the controversy surrounding the atomic bomb missions. Another significant survivor is Bockscar, the aircraft that bombed Nagasaki, displayed at the National Museum of the United States Air Force in Dayton, Ohio. A third notable survivor is a B-29 displayed at the Strategic Air Command and Aerospace Museum in Nebraska, painted in the markings of the 509th Composite Group that flew the atomic missions. The B-29's technological influence extended far beyond World War II. The pressurized cabin became standard on all subsequent large aircraft, military and civilian. The remote-controlled turrets influenced defensive systems for the next generation of bombers. The high-altitude performance requirements drove engine development that enabled the post-war generation of jet aircraft. Soviet engineers studied the B-29 extensively. 3 B-29s made emergency landings in Soviet territory in 1944 after bombing missions over Japan launched from bases in China. The Soviets interned the aircraft and crews then reverse-engineered the B-29 to create the Tupolev Tu-4, a near-exact copy. The Tu-4 served as the Soviet Union's primary strategic bomber until the mid-1950s. The B-29 represented the pinnacle of piston engine bomber design. It incorporated every advanced technology available in 1942: pressurized cabins, remote-controlled armament, high-altitude engines, advanced aerodynamics, complex systems integration. The aircraft cost $639 per unit in 1945 dollars, equivalent to approximately $10 million in 2024 dollars, making it one of the most expensive single aircraft programs in history when adjusted for inflation. The total program cost of $3 billion bought 370 aircraft and the infrastructure to support them. It also bought strategic capability that no other nation possessed in 1945: the ability to strike any target in the world from secure bases operating at altitudes where interception was difficult, carrying sufficient bomb loads to destroy strategic targets. This capability gave the United States a strategic advantage that lasted until the Soviet Union developed similar capabilities in the early 1950s. During that 5-year window, American B-29s armed with atomic weapons represented the only credible strategic deterrent in the emerging Cold War. The B-29's legacy was its demonstration that technology could create decisive operational advantages. The pressurized cabin allowed crews to operate at altitudes where enemy defenses were ineffective. The centralized fire control system provided defensive firepower without the weight and complexity of manned turrets. The powerful engines and aerodynamic efficiency provided range that put any target within reach. These capabilities came at enormous cost: $3 billion, 47 aircraft lost in training accidents, 136 lost in combat, thousands of hours of engineering development, but the capabilities changed strategic bombing from a tactical expedient to a war-winning strategy. Boeing B-29 Superfortress. Wingspan 141 feet length, 90 to 9 feet empty weight, 74 width 500 pounds, maximum speed 358 miles per hour, service ceiling 33 to 600 feet range, 3,250 miles with 5,000-pound bomb load. The pressurized fortress that flew above the fighters operated where no other bomber could operate, carried the atomic bombs that ended the war. 3,970 aircraft built, 147 lost to combat, 512 lost to operational accidents, 24,000 tons of bombs dropped on Japan, 67 cities burned. The most expensive weapons program of World War II that proved technology could overcome numerical inferiority. The bomber that flew so high that enemy fighters gasped for air trying to reach it, that operated in shirt sleeves at altitudes where other crews would have died in minutes, that demonstrated pressurization and remote-controlled weapons were not science fiction, but operational reality. The superfortress that rewrote the rules of strategic bombing and dominated the sky until jets made pistons obsolete.